All right, guys, welcome back to the third and final section on this concussion pathophysiology and injury biomechanics article. It's published in the current reviews in musculoskeletal medicine, and then obviously it's cited at the bottom so that you can follow along. This is one that I think will be a little bit more pertinent to you guys because a lot of you ask about the biomechanics, and we've already gone over two of the previous sections, so we can put those down in the description. But the introduction is the same as the other other two. So I'm not going to insult your intelligence and read this. I just wanted to let you know that there is we are talking about mild traumatic brain injuries instead of all other type of brain injuries. Okay, so this article is specifically talking about the pathophysiology and injury biomechanics of mild traumatic brain injury or concussion. And this is the definition that they give in the article. Okay, so this subsection, the biomechanics, starts off with linear acceleration and talking about how it plays a role in brain injury. So there's a couple of things to make sure that we understand first. One is the difference between velocity and acceleration. So velocity is a vector quantity, right? So it has a direction and a magnitude. The magnitude here would be speed. So typically you see it referred to as meters per second. And then acceleration is a step further. So it's velocity over time. So it's meters per second squared typically. So think about, I'm sure you've heard the term terminal velocity. So if you drop something off of a really tall building, it accelerates, right, at 9.82 meters per second squared. And then taking away wind resistance, it stops accelerating and it just stays at the same speed. So it still has velocity, but it has stopped accelerating. That's what we mean by acceleration. And so early on in the research, it started talking about when they started to look at these things and measure what is happening at the skull and as a proxy, the brain, linear acceleration in either the forward motion or side to side, so really flexion and extension in the sagittal plane, or lateral flexion in the frontal plane or the coronal plane, was associated with an increase in intracranial pressure. And what that is just the pressure that the fluid, mostly cerebrospinal fluid, is putting on the structures in neural tissue of the brain. And so it seems pretty intuitive that if we see the increase in intracranial pressure with an increase in linear acceleration, and we can correlate those two, and we know that the increase in intracranial pressure can cause neurological dysfunction, that we are making that association. Okay, so that was some of the early research. And then they also went on to look at the level of dysfunction. And so it seemed that the level of dysfunction seemed to correlate with the higher levels of intracranial pressure. So the higher the acceleration, the higher the intracranial pressure directly after the insult or the injury, and then the higher level of the dysfunction. These were a lot in animal models, but then we start to get this shift from linear acceleration to rotational acceleration in animal models. And so they started to look at, okay, so what happens in a more rotational plane or more if we look at more triplanar movements, if we induce a triplanar movement injury to an animal. And it looked like in the beginning that it started to create more significant intracranial pressure changes in the positive direction than linear acceleration. So then they started looking at rotational acceleration and the role that plays. And the early research was looking at the tensile and shear forces on the nervous system. This is when we're going to start to shift into what I've been talking about in several of my different videos about what causes the acute loss of consciousness in a knockout and what may be able to explain some of the ongoing symptoms after concussion. And so they were able to kind of figure out that brain or neural tissue easily deforms when you expose it to these types of forces. It's not like bone where if you do it up to a certain point and allow it to recover, that it actually gets a little bit stronger. Neural tissue does not behave this way. And so even the more recent models were able to support this relationship between rotational forces and strain to the neural tissue or deformation in the neural tissue. And again, that phenomena they think is, the research is being developed still, but they think it's called mechanoporation. These tiny pores in the axon specifically, or the white matter, are with those shear and tensile forces disrupt some of the signal transmission. Okay. So then we move on to what is more likely to cause, and we see this a lot in the literature. You start with one thing, you start to mold it into something else, and then you find out that it's probably a combination or some variation or gradation of the two. So it's very hard to isolate rotational acceleration from linear acceleration, particularly in vivo or in humans. So in live, in vivo just means in live, either animals or humans or whatever. Since it's very difficult to isolate that, we have to use a proxy measure, and the best proxy measure that we have is measuring the rotation of the fixed structures of our skull and measuring those, and then looking at what may happen before and after in functional fMRI imaging or other really advanced neuroimaging techniques that they have. So both linear acceleration and rotational acceleration are almost always present in M2BI, which is intuitive because we don't live in planar motions. Almost all of our motions are triplanar, meaning that we perform them in the sagittal plane, the coronal plane, which we talked about before, the frontal plane, and the rotational plane. Almost all of our movements, since we're three-dimensional, we move in that way. So each play a role in these mild traumatic brain injuries, and these theoretical models are attempting to associate the degree of linear acceleration and rotational acceleration, which one plays maybe a bigger role, and then associate them with the risk for injury. So whenever we see these things happen, what can it tell us about maybe the severity or the nature of the injury? Okay, so now we've already reached the discussion. This is a little bit of a shorter talk. As always, we're going to go into some implications for training after this. So if you followed this far already and you want to know more, I have a Patreon account where I talk for several minutes about maybe how this the implications of your training and how it can inform your training in order to stay healthier. And it's $5 a month. It's very, very accessible. I don't want that to be a way that, again, don't do it if you can't afford it. But we also have some sections where you can ask anything biomechanical related. We've already had some questions about strength and conditioning as it relates to their training. So my hope is to create a really well-informed community and not have something that costs a lot of money. Okay. So the first point, we'll just go through what we talked about and wrap it up in a nice, neat bow here. Linear acceleration was correlated with increased intracranial pressure in the beginning of their research. So whenever they started to look at mild traumatic brain injuries or traumatic brain injuries as a whole. It also plays a role with rotational acceleration. So intracranial pressure, which has been correlated with cognitive dysfunction neurological dysfunction, one of those being cognitive delays after an injury. Rotational acceleration seems to create more tensile and shearing in neural tissue than linear acceleration, although both of them seem to play a pretty significant role. So development of the risk injury models or injury risk models are underway. It's very hard to separate how much linear acceleration versus rotational acceleration are playing a role, being that they're almost impossible to separate in vivo and measure. It goes on to talk about some of the different ways that you can measure those, but those are a little bit beyond my scope. I am familiar with some of the ways, but a lot of that math is pretty advanced. So I'm not in a program, a PhD in biomechanics or master's in biomechanics program. So I'm not even going to kind of pretend to do that. But that's pretty much it for this section. If you're part of the Patreon, go over to the Patreon and you'll see the rest of this. But for the rest of you guys, thanks for watching. Tell me what you think in the comments.